let yourself settle in for a moment. Find that comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders. Take a slow breath, feeling the air move through you, and as you exhale, let any tension drift away like smoke dispersing in the evening air. Tonight, we're going on a journey unlike any other, a journey to the edge of reality itself and perhaps beyond. Just close your eyes if you'd like, or let them rest gently on a distant point, and allow the story to unfold around you like a gentle tide. We're going to explore one of the universe's most profound mysteries, a question that sits at the intersection of physics, philosophy, and imagination. What would happen if you fell into a black hole, and could that fall somehow lead to the birth of an entirely new universe? The edge of understanding. Black holes occupy a peculiar place in our imagination. They are simultaneously the most exotic objects we know to exist, and yet fundamental components of the cosmos, lurking at the centers of galaxies, shaping the evolution of the universe on the grandest scales. They represent boundaries, thresholds where our normal understanding of space and time breaks down, where the familiar rules that govern our daily existence cease to apply in any recognizable way. When we think about black holes, we often picture them as cosmic vacuum cleaners, indiscriminately devouring everything that comes near them. But this image, while vivid, misses something essential about their nature. Black holes are not really holes at all. They're regions of space-time where gravity has become so intense, so overwhelming, that it fundamentally changes the nature of reality itself. They're places where space and time swap roles, where cause and effect become tangled in ways that challenge our deepest intuitions about how the universe works. For most of human history, we had no concept of such objects. The ancient Greeks imagined the cosmos as a series of nested crystalline spheres. Medieval scholars thought of the heavens as perfect and unchanging. Even when Isaac Newton gave us his law of universal gravitation in the 1600s, describing how every mass attracts every other mass, nobody imagined that gravity could become so extreme that it would trap light itself. The possibility of black holes emerged from the mathematics of general relativity. Albert Einstein's revolutionary theory published in 1915. Einstein showed that gravity wasn't a force pulling objects together, as Newton had thought, but rather a consequence of how mass and energy warp the fabric of space-time itself. Massive objects create curves and dimples in this fabric, and other objects moving through space-time naturally follow these curves, which we perceive as gravitational attraction. Just months after Einstein published his field equations, a German physicist named Karl Schwarzschild, while serving in the German army during World War I, found an exact solution to Einstein's equations. Schwarzschild was calculating the gravitational field around a perfectly spherical, non-rotating mass, and what he discovered was remarkable. His solution showed that if you compressed enough mass into a small enough radius, something extraordinary would happen. There would be a boundary, a sphere surrounding the mass, from which nothing, not even light, could escape. This boundary would sit at what we now call the Schwarzschild radius, and it would mark the edge of a black hole. Schwarzschild himself didn't think such objects could actually exist in nature. Einstein himself resisted the idea. In 1939, Einstein published a paper arguing that black holes were impossible, that natural processes would never allow matter to collapse to such extreme densities. But that same year, Robert Oppenheimer and his student Hartland Snyder published their own paper showing that When a sufficiently massive star exhausted its nuclear fuel, nothing could prevent it from collapsing into a black hole. The implosion, they showed, would be inevitable. Even then, it took decades for the physics community to fully accept black holes as real objects rather than mathematical curiosities. The term black hole itself wasn't coined until 1967 by physicist John Wheeler, who needed a catchier phrase than gravitationally completely collapsed object for a lecture. But by the 1970s, the evidence had become overwhelming. Astronomers were detecting objects with the exact properties predicted for black holes, regions of space where something massive and invisible was affecting nearby stars and gas. Today, we've even captured images of the glowing accretion disks surrounding black holes, and we've detected the gravitational waves produced when black holes collide and merge. Yet, despite all we've learned, black holes remain deeply mysterious. The most profound mystery concerns what happens at their very centers, at what physicists call the singularity, and what might happen to anything that falls in. According to the classical predictions of general relativity, matter falling into a black hole would be crushed to infinite density at a single point, a place where the curvature of space-time becomes infinite, where the known laws of physics simply stop working. But here's where things become truly fascinating. In recent decades, some physicists have proposed that the story doesn't end at the singularity. Drawing on extensions of general relativity that incorporate quantum mechanical effects, they've suggested that what looks like an ending from our perspective might actually be a beginning from another perspective. They've proposed that the interior of every black hole might give rise to an entirely new universe, complete with its own space, its own time, and its own physics. If this is true, then our own universe might exist inside a black hole in some larger parent universe, and every black hole in our cosmos might contain within it an entire cosmos of its own. This is not science fiction. This is serious theoretical physics, based on rigorous mathematics and consistent with everything we currently know about the universe. The scenario is speculative, yes, and it remains unproven, but it's grounded in real physics, an attempt to extend our theories into regimes where they've never been tested before. So, tonight, we're going to take that journey. We're going to imagine what it would be like to fall into a black hole, to experience firsthand the warping of space and time, to cross the event horizon, to descend toward the singularity, and to explore the possibility that this descent might somehow transform into the birth of a new universe. Along the way, we'll encounter some of the strangest phenomena in physics, from time dilation and spaghettification to quantum mechanics and the fabric of space-time itself. This is a journey to the limits of human knowledge, to the boundary between what we know and what we can only imagine. It's a journey that will challenge your intuitions about reality, about time, about the nature of existence itself. But it's also, in its own way, a profoundly hopeful story, one that suggests the universe might be far stranger, far richer, and far more generative than we ever imagined. So let's begin. Let's imagine that you're an intrepid explorer, equipped with an indestructible spacecraft and an insatiable curiosity. You've decided to do what no one has ever done before, to dive into a black hole and see what lies within. Your destination is a supermassive black hole, millions of times more massive than our Sun, sitting at the center of a distant galaxy. You've chosen a supermassive black hole rather than a smaller, stellar mass black hole for a very good reason. With a smaller black hole, the tidal forces at the event horizon would tear you apart before you ever got inside. But with a supermassive black hole, the event horizon is so vast, the curvature of space-time so gentle at that scale, that you could cross it intact, your body whole, your consciousness preserved, at least for a while longer. Your spacecraft approaches the black hole from a safe distance, millions of kilometers away, where its gravity is strong but manageable. From here, you can see the monster at the heart of the galaxy, though not directly. What you see is the accretion disk, a vast, swirling maelstrom of gas and dust spiraling inward, heated to millions of degrees by friction and compression, blazing with radiation across the electromagnetic spectrum. The disk glows with an angry red-orange light near its outer edges, shifting to white-hot brilliance toward the center. At the very center, where the material approaches the event horizon, there's darkness, a perfect black circle, the shadow of the black hole itself. This shadow is larger than you might expect. It's not just the event horizon. Light can actually orbit the black hole at a radius about 1.5 times the Schwarzschild radius, trapped in unstable circular orbits before either falling in or escaping to infinity. This creates a region called the photon sphere, and from your vantage point, it appears as an expanded shadow, a region of darkness surrounded by a brilliant ring where the light from the accretion disk is focused and intensified by the black hole's gravity. The view is both beautiful and terrifying. The accretion disk doesn't look like a simple flat disk from your perspective. The black hole's gravity bends the light traveling from the far side of the disk, curving it up and over the black hole so that you can see both the top and bottom of the disk simultaneously. It's as if the disk has been folded in a way that defies normal, three-dimensional geometry. You're seeing space-time's curvature made visible, the warping of light paths by gravity, a phenomenon called gravitational lensing. But you're not here to observe from a distance. You came to go inside. You fire your engines and begin your descent, approaching the event horizon, where time and space begin to blur. As your spacecraft accelerates toward the black hole, the first changes are subtle. The black hole's gravity begins to pull on you more strongly, but this is something you've experienced before in various forms. Gravity on Earth, gravity on other planets, even the gentle tug of your spacecraft's acceleration, these are all familiar sensations. But as you draw closer, within a few 100,000 kilometers of the event horizon, something strange begins to happen. Something that has no analog in your everyday experience. You're carrying with you a collection of synchronized atomic clocks, the most precise timepieces humanity has ever created, accurate to within billionths of a second. Before you left, you synchronized all these clocks with clocks that remained back on Earth, back in the galaxy far from the black hole's influence. Now, as you monitor the signals from those distant clocks, you notice they're running fast, faster and faster, ticking off seconds and minutes and hours at an accelerating rate. It's not that those clocks are malfunctioning, it's that time itself is passing at different rates in different parts of the universe. This is gravitational time dilation, one of the most profound predictions of general relativity, and one that's been verified countless times in experiments here on Earth and in space. Time passes more slowly in stronger gravitational fields, as measured by observers in weaker fields. The effect is tiny in most circumstances. If you spend your entire life on Earth's surface rather than at a higher altitude, you'll age about 100 nanoseconds less than you would have otherwise, far too small to notice. But near a black hole, the effect becomes dramatic. From your perspective, your own clocks are ticking normally. Each second feels exactly like a second to you. But when you look at the signals from the clocks back in the distant galaxy, you see them racing ahead. In the time it takes for 1 second to pass on your spacecraft, multiple seconds, then minutes, then hours pass back home. And the closer you get to the event horizon, the more extreme this effect becomes. At the same time, something equally strange is happening to the light from the accretion disk and the distant stars. As photons climb out of the black hole's gravitational well to reach your eyes, they lose energy, a phenomenon called gravitational redshift. Light that was emitted as blue shifts toward red, then infrared, then radio waves. Meanwhile, light coming from ahead of you, from matter falling into the black hole, is blue shifted, boosted to higher energies. The universe seems to be rearranging itself around you, colors shifting, the spectrum of reality transforming. But perhaps the most disorienting effect is what happens to the appearance of the cosmos itself. As you approach the black hole, moving at an appreciable fraction of the speed of light, special relativistic effects combine with gravitational lensing to create a view unlike anything human eyes have ever seen. The stars ahead of you seem to concentrate into a bright ring, compressed by aberration and gravitational lensing. Behind you, the view seems to expand, but also to dim and redden. The black hole is warping not just your path through space, but the paths of every beam of light around you, bending the fabric of the universe into new configurations. If you could somehow look back at the galaxy you came from, you would see something extraordinary and disturbing. Time would appear to be accelerating there, unfolding at a frantic pace. Stars would burn through their life cycles in what seemed like moments. Civilizations would rise and fall. Billions of years of cosmic history would flash past in subjective hours. You're watching the universe age, watching time itself flow at a different rate, separated from the normal flow of events by the increasing curvature of space-time. This asymmetry is one of the most mind-bending aspects of black holes. To observers back in that distant galaxy, if they had powerful enough telescopes to watch you, they would see something very different. They would see your spacecraft slowing down as it approached the event horizon, moving more and more sluggishly, your clock ticking slower and slower. They would see you redden and dim, the light from your ship stretched to longer and longer wavelengths as it climbed out of the deepening gravitational well. They would see you asymptotically approach the event horizon, never quite reaching it, frozen in time at the threshold. This is not an illusion or a trick of perception. Both perspectives are equally valid. Time is genuinely passing at different rates in different locations, and there's no absolute universal time that would adjudicate between these perspectives. This is the nature of relativity, the profound lesson that Einstein's theories teach us. Time and space are not fixed, absolute backgrounds against which events unfold. They're dynamic, flexible, participant players in the cosmic drama. As you cross into the region within a few Schwarzschild radii of the event horizon, the tidal forces begin to make themselves known. Tidal forces arise whenever there's a gradient in gravity, whenever the gravitational pull on one part of an object differs from the pull on another part. On Earth, these forces are what create ocean tides, as the moon's gravity pulls more strongly on the side of Earth facing it than on the far side. Near a black hole, tidal forces become extreme. These forces would attempt to stretch you along the direction toward the black hole while simultaneously squeezing you from the sides. If you're oriented feet first toward the black hole, your feet experience stronger gravity than your head, and this difference creates a stretching force. At the same time, because everything is being pulled toward the same center point, there's a slight inward compression from the sides. For a stellar mass black hole, a black hole with a mass just a few times that of the Sun, these tidal forces at the event horizon would be catastrophically strong. Long before you reached the horizon, they would exceed the tensile strength of any known material, indeed, the binding strength of atomic matter itself. You would be torn apart, stretched into a long thin stream of particles, in a process that physicist Stephen Hawking colorfully termed spaghettification. But you chose a supermassive black hole precisely to avoid this fate. For a black hole with a mass of millions or billions of solar masses, the event horizon is correspondingly larger, and the curvature of spacetime at the horizon is gentler. The tidal forces at the event horizon of a supermassive black hole are actually quite mild, no stronger than the tidal forces you experience on Earth's surface from the Moon. You could cross the event horizon of a supermassive black hole without feeling any discomfort, without even knowing that you've passed the point of no return. This is a crucial point that's often misunderstood. The event horizon is not a physical surface. It's not a membrane or a wall. It's a mathematical boundary in spacetime, a point of no return defined by the fact that the escape velocity there equals the speed of light. From inside the event horizon, even a beam of light directed outward would fall back in, and since nothing can travel faster than light, nothing can escape. But crossing the horizon itself is, locally, uneventful. There's no there, no marker that says you have now entered a black hole. Yet something profound has changed. You have crossed a threshold, past a point of no return in the most literal sense possible. The structure of spacetime itself has undergone a fundamental transformation, crossing the event horizon, where reality inverts. To understand what happens when you cross the event horizon, we need to think carefully about the nature of spacetime itself. In the region outside the black hole, space is space and time is time in more or less the familiar ways. You can move forward or backward, left or right, up or down through space, though gravity makes some directions easier than others, and you move forward through time, from past to future, inevitably and irreversibly. But the mathematics of general relativity reveal something astonishing about the region inside the event horizon. The roles of space and time undergo an exchange, a swap. What was a direction in space outside the horizon becomes a direction in time inside it, and vice versa. Outside the event horizon, the radial direction, the direction toward or away from the black hole's center, is a direction in space. You can, in principle, move outward away from the black hole or inward toward it, and you can stop at any radius you choose, provided you have sufficient thrust. The time coordinate, meanwhile, advances inexorably from past to future. You can't stop time, can't reverse it, can't avoid moving forward through it. Inside the event horizon, these roles flip. The radial direction becomes time-like. Moving toward the singularity at the center is no longer a spatial direction you can choose to move in or not. It becomes as inevitable as the passage of time itself. The singularity is not a place in space that you're moving toward. It's a moment in your future, an event that lies ahead of you in time, unavoidable and inevitable. You're not so much falling toward the singularity as you are being carried forward through time toward an encounter that cannot be prevented. Meanwhile, one of the directions that was temporal outside now becomes spatial inside. In a very abstract sense, the direction that pointed from past to future, outside the horizon, now points in a spatial direction, inside. This is difficult to visualize because it's so far outside our everyday experience, but it has profound implications. For one thing, it means that causality, the relationship between cause and effect, gets scrambled inside a black hole in ways that make no sense in terms of our ordinary understanding. Effects can precede their causes. Light cones, the boundaries that define what regions of space-time can causally influence each other, tip over and point inexorably toward the singularity. Every path you might take, every possible trajectory through the warped space-time inside the event horizon, terminates at the singularity in your future. If you could look around after crossing the event horizon, if your eyes could still receive and process light in any meaningful way, you would see impossible things. Light that fell in before you would still be propagating, still be moving, but its path would be constrained to move inward, toward the singularity. You might see ghostly images of things that entered the black hole in the distant past, their light trapped in complicated orbits within the event horizon. You might see multiple distorted images of the same object, light that's taken different paths through the curved space-time to reach your eyes. The view behind you, looking back the way you came, would be even stranger. The event horizon from inside is not dark. In fact, you might still see the outside universe, but only in a shrinking region of sky. All the light from the outside cosmos would be concentrated into a diminishing bright spot, a tunnel-like view of everything beyond the horizon. And in that bright spot, you would see time accelerating even more dramatically than before. The entire remaining history of the universe would unfold before your eyes, compressed into a shrinking field of view. Stars would be born and die. Galaxies would collide and merge. The cosmic expansion would continue, carrying distant galaxies over the horizon of the observable universe. Though this is what some theoretical calculations suggest, the reality would likely be more complicated and more disorienting. The intense gravitational effects, the extreme blue shifting of any radiation falling in with you, the quantum mechanical effects that come into play in such extreme conditions, all these would create an environment unlike anything we can easily imagine or describe. As you continue to fall inward, deeper inside the event horizon, the tidal forces that were gentle at the horizon begin to grow. They increase rapidly, inexorably, because the curvature of space-time is becoming ever more extreme. The difference in gravitational pull between your head and your feet, which was negligible at the horizon, begins to mount. The stretching force along your body and the compressive force from the sides intensify. Even in a supermassive black hole, there's a limit to how far you can fall before these forces become overwhelming. The calculations are complex, depending on the exact mass of the black hole and your distance from the singularity. But eventually, the tidal forces will exceed the limits that your body can withstand. The molecular bonds holding your cells together will fail. The atomic structures will begin to deform. You will be stretched and compressed, spaghettified, reduced to a stream of elementary particles. But let's imagine, for the sake of our journey, that you're somehow protected from these forces, that your spacecraft has some magical shielding that preserves you intact. Or perhaps we should imagine that you're not a fragile biological organism, but some kind of indestructible probe, a witness made of mathematics and curiosity rather than flesh. Either way, the question remains, What happens as you approach the singularity? The singularity, where physics breaks down. According to the classical theory of general relativity, the space-time at the very center of a black hole contains a singularity. This is a point, or in the case of a rotating black hole, a ring where the curvature of space-time becomes infinite, where the density of matter becomes infinite, where all the matter that has ever fallen into the black hole is compressed to zero volume. These infinities are deeply troubling to physicists. They represent the breakdown of the theory itself, a signal that general relativity, as powerful and successful as it is not telling us the complete story. The theory produces predictions that are mathematically well-defined at the singularity, but physically nonsensical. Infinite density, infinite curvature, these are not things that can exist in a meaningful physical sense. This problem was put on rigorous mathematical footing by Roger Penrose and Stephen Hawking in their famous singularity theorems, developed in the 1960s and early 70s. Penrose proved that once an event horizon forms, a singularity is inevitable, regardless of the symmetry or specific details of the collapse. Hawking extended these results, showing that the Big Bang itself, if we run the expanding universe backward in time, must also have begun from a singularity. These theorems were remarkable achievements, and they earned Penrose a share of the 2020 Nobel Prize in Physics. But the singularity theorems come with an important caveat. They are theorems of classical general relativity, a theory that describes gravity in terms of the smooth, continuous curvature of space-time. They don't account for quantum mechanics, the theory that governs physics at the smallest scales, where the smooth fabric of space-time dissolves into something more grainy, more uncertain, more fundamentally probabilistic. Most physicists believe that quantum mechanics must somehow modify the classical picture of black holes, particularly in the region near the singularity where the curvature becomes extreme. The problem is that we don't yet have a complete theory of quantum gravity, a theory that successfully merges general relativity with quantum mechanics. We have candidate theories, string theory, loop quantum gravity, and others, but none has been conclusively verified, and they make different predictions about what happens at the singularity. One common expectation is that quantum effects will smear out the singularity somehow, preventing the curvature from becoming truly infinite. Instead of all the matter being crushed to a point, quantum mechanical uncertainty might establish a minimum length scale below which our classical notions of space and time cease to make sense. This minimum length is expected to be the Planck length, about 10 to the power of minus 35 meters, a scale so small that it's meaningless to talk about distances shorter than this. At this scale, space-time itself becomes a roiling quantum foam, a probabilistic blur where the concepts of distance and duration lose their meaning. The singularity, rather than being a point of infinite density, might be a small but finite region where quantum fluctuations dominate, where spacetime itself is fluctuating wildly, constantly creating and destroying tiny virtual black holes and wormholes in a chaotic quantum dance. But some physicists have proposed something even more radical. They've suggested that the singularity might not be an ending at all, but a transition, a bridge to something else. And this is where the possibility of black holes giving birth to new universes enters the picture. Einstein-Cartan theory, torsion, bounce, and cosmic birth. The theory that allows black holes to become cosmic wombs is called the Einstein-Cartan theory, or more formally, the Einstein-Cartan-Sciama-Kibble theory. It's an extension of general relativity that incorporates an additional geometric property of spacetime called torsion. To understand torsion, it helps to think about the difference between bending and twisting. Imagine a flexible rod. You can bend it, creating curvature, which is what general relativity describes. But you can also twist it, and this twisting represents torsion. Ordinary general relativity assumes that the connection between nearby points in spacetime is symmetric, which mathematically corresponds to zero torsion. Einstein-Cartan theory relaxes this assumption, allowing spacetime to have both curvature and torsion. The theory was first proposed by the French mathematician Einstein-Cartan in 1922, just a few years after Einstein published general relativity. Einstein himself became interested in the idea in the late 1920s, exploring whether torsion might have something to do with electromagnetism as part of his quest for a unified field theory. That particular line of inquiry didn't pan out, and Einstein eventually abandoned it. The idea was revived in the 1960s by Dennis Sciama and Thomas Kibble, who showed how torsion could couple to the intrinsic spin of matter. In quantum mechanics, particles carry an intrinsic angular momentum called spin. It's not that the particles are literally spinning like tiny tops. Spin is a fundamental quantum property that has no classical analog, but it behaves mathematically like angular momentum. In Einstein-Cartan theory, this spin couples to the torsion of spacetime. Where there is matter with spin, particularly fermionic matter like electrons, protons, and neutrons, there is torsion in spacetime. Under normal circumstances, at ordinary densities and energies, this torsion is utterly negligible. Its effects are far too small to detect. But at the extreme densities that exist inside black holes or that existed in the very early universe, torsion becomes significant. And when it does, something remarkable happens. The coupling between spin and torsion generates a repulsive force, a kind of anti-gravity that opposes the crushing gravitational collapse. This repulsive force is not some ad hoc addition to the theory. It emerges naturally from the mathematics when you properly account for the conservation of angular momentum in a spacetime with torsion. The spin of particles interacts with the torsion in such a way that it creates an effective pressure, a resistance to further compression. In 2010, physicist Nikodym Popławski, working first at Indiana University and later at the University of New Haven, developed detailed models of what would happen to matter collapsing inside a black hole according to Einstein-Cartan theory. His calculations showed that as matter falls inward and the density increases, the torsional repulsion would eventually become strong enough to halt the collapse before a singularity could form. Instead of crushing down to infinite density at a point, the matter would reach a maximum density, perhaps 10 to the power of 96 kilograms per cubic meter, vastly greater than nuclear density, but still finite. At this point, the gravitational collapse would stop and reverse. The matter would bounce, recoiling from this maximum density and beginning to expand again. But here's the crucial part. This bounce and expansion wouldn't happen back into the universe from which the matter fell. Remember that inside the event horizon, all paths lead inward, toward the singularity. There's no going back the way you came. Instead, according to Einstein-Cartan theory, the bounce would create new space, new time, a new region of spacetime that expands into itself. From our perspective outside the black hole, this new region would remain hidden behind the event horizon, forever separated from our universe. But from within that new region, it would be a big bounce, the beginning of a new universe. This new universe would not emerge from a singularity, from a point of infinite density and zero size. It would emerge from a bounce at finite maximum density. This is an important distinction. One of the problems with the traditional Big Bang scenario is the singularity at the beginning of time. Einstein's equations predict that if we run the expanding universe backward, it must have started from a state of infinite density and temperature, a singularity where the laws of physics break down. But Einstein-Cartan theory replaces this singular Big Bang with a non-singular Big Bounce. The new universe created inside the black hole would initially be very small and very dense, but it would expand, just as our universe is expanding. It would cool as it expanded, allowing particles to form, then atoms, then eventually stars and galaxies. It would, in every sense that matters, be a complete universe, with its own space, its own time, its own arrow of causality pointing from past to future. From the perspective of the parent universe, the universe where the black hole formed, none of this would be visible. The event horizon would remain intact. The black hole would appear to be simply a black hole, sitting there in space, perhaps accreting matter from its surroundings, perhaps merging with other black holes, but giving no hint of the cosmos contained within. From the perspective of observers inside the new universe, once it had expanded and cooled enough for structure to form, for complexity to emerge, for life and consciousness to evolve, they would look out at their cosmos and see an expanding universe stretching away to a cosmic horizon. They might develop physics and astronomy. They might discover the cosmic microwave background, the echo of their big bounce, the radiation left over from when their universe was hot and dense. They might puzzle over the origin of their cosmos, wondering what came before, or whether before even makes sense. And if their physicists developed sufficiently advanced theories, they might realize that their universe could itself contain black holes, and that each of those black holes might contain new universes in turn. They might realize they were living inside a black hole in some larger parent universe, the multiverse of black holes, infinite recursion and observable predictions. If Einstein-Cartan theory is correct, or if some other quantum theory of gravity allows black holes to give birth to new universes through a similar mechanism, then the structure of reality is far more elaborate than we ever imagined. Every black hole would be a doorway to a new universe. Our universe would itself be inside a black hole in some parent universe. And that parent universe would be inside another black hole in another parent universe, and so on, potentially infinitely. This creates a kind of cosmic tree, a branching structure where each universe contains multiple black holes, and each black hole spawns a new universe. The number of universes in this tree would grow exponentially with each level. If our universe contains, say, 1,000,000,000,000,000 black holes, a very rough estimate, then there would be that many child universes spawned from our universe. And each of those would spawn billions of trillions more. The total number of universes in this multiverse would be staggering, effectively infinite in any practical sense. This isn't just abstract speculation. If we're living inside a black hole in a parent universe, then there might be observable consequences, predictions that we could test. One key prediction has to do with the initial conditions of our universe. In the traditional Big Bang picture, the uniformity and flatness of the universe seem like fine-tuned coincidences. Why did the universe start out so smooth and homogeneous? Why is its geometry so close to flat? The standard answer involves a period of cosmic inflation, an exponential expansion in the first fraction of a second after the Big Bang. In the black hole universe scenario, inflation might be a natural consequence of the bounce. Popłowski showed that the extreme conditions near the bounce, the coupling between torsion and spin, could naturally drive a period of rapid expansion that would smooth out irregularities and flatten spacetime. The bounce itself would provide the energy and the mechanism for inflation, eliminating the need to postulate inflation as a separate, independent process. Another prediction has to do with the overall geometry and topology of spacetime. In Einstein-Cartan theory, the interior of a rotating black hole has a preferred direction of rotation, inherited from the angular momentum of the collapsing matter that formed the black hole. This preferred direction could potentially be carried over into the new universe created inside, establishing a preferred axis in the cosmos. Our universe does indeed show hints of such preferred directions, though the evidence is controversial. Some studies of the cosmic microwave background radiation have found weak alignments and asymmetries that seem to violate the expectation of perfect statistical isotropy. These anomalies are sometimes called the axis of evil, though that's a somewhat tongue-in-cheek name for what are actually very subtle effects. If real, they might be signatures of the rotation of the parent black hole in which our universe is embedded. The scenario also makes predictions about the values of physical constants. If universes are created inside black holes, and if the laws of physics can vary slightly from one universe to another due to different symmetry breaking or different vacuum states, then there would be a kind of natural selection among universes. Universes that produce lots of black holes would have many offspring universes. Over time, the multiverse would be dominated by universes whose physical constants are tuned to maximize black hole production. Interestingly, our universe does seem to be reasonably good at making black holes. Stars form readily. Massive stars collapse into stellar mass black holes. Galaxies contain supermassive black holes at their centers. A universe with slightly different constants might not form stars at all, or might have stars that never collapse, or might expand so fast that structures never form. From this perspective, the apparent fine-tuning of our universe's constants might not be a coincidence or a consequence of anthropic selection. The idea that we observe these values because they're necessary for our existence. Instead, it might be cosmic natural selection, with the constants tuned to maximize reproductive success at the universal level. This is deeply speculative, of course, and many physicists remain skeptical. The Einstein-Cartan theory itself is not widely accepted as the correct extension of general relativity, though it has passionate advocates. The coupling between torsion and spin has never been detected experimentally, though that's not surprising given how weak the effects would be except under extreme conditions. The idea that black holes create new universes remains highly controversial and is far from being established science. But it's important to emphasize that this is not pseudoscience or mysticism. This is physics, grounded in the same mathematical framework that has given us GPS satellites, gravitational wave detectors, and our understanding of the cosmos. The equations are rigorous, the reasoning is careful, and the predictions are, in principle, testable. It might be wrong, but it's not crazy. The nature of time. Inside a black hole universe. One of the most puzzling aspects of the black hole universe scenario is how to think about time. From the perspective of the parent universe, the one where the black hole exists, any new universe created inside the event horizon is frozen in time. Because of the extreme time dilation near the event horizon, an external observer would never see the interior universe evolve. The formation of the event horizon and whatever happens inside would be infinitely far in the future as measured by external clocks. Yet, from the perspective of observers inside the new universe, time flows normally. They experience a past, present, and future. Their universe expands, cools, forms structures, evolves. They can measure the age of their universe, currently estimated at 13.8 billion years for our cosmos. How can these perspectives be reconciled? The resolution lies in understanding that there is no universal, absolute time. Time is always measured relative to a particular reference frame, a particular world line through space-time. The time experienced by observers inside the black hole is their proper time, the time measured by clocks moving along with them. This proper time is perfectly real and meaningful, even though it corresponds to an infinite time coordinate as measured from outside the event horizon. This is similar to what happens at the event horizon itself. An infalling observer crosses the event horizon in finite proper time, experiencing nothing special at that moment. But to an outside observer, the crossing happens infinitely far in the future. Both descriptions are valid in their respective reference frames. They are describing the same events from different perspectives, and general relativity tells us how to translate between these perspectives. Inside the new universe, causality works normally. Effects follow causes. The arrow of time points from past to future. The laws of physics, including the second law of thermodynamics, operate as expected. The residents of this universe would have no direct evidence of being inside a black hole. They would see their universe as a self-contained cosmos, complete unto itself. However, there might be subtle clues. If the new universe inherits some properties from the parent universe, such as the rotation of the black hole, these could appear as cosmological anomalies, as departures from perfect isotropy or homogeneity. The initial conditions at the bounce might also carry information about the parent universe, encoded in the distribution of matter and energy, the spectrum of primordial density fluctuations, the relative abundances of different particle species. Some researchers have speculated about whether information could be transmitted from parent universe to child universe through the black hole interface. In conventional general relativity, information falling into a black hole is lost, destroyed at the singularity, or perhaps leaked, out slowly through Hawking radiation, but in thoroughly scrambled form. But in models where the singularity is replaced by a bounce, information might pass through, carried by the matter and fields that undergo the bounce. If so, then the initial conditions of the child universe might contain encoded information about the parent universe. This information would be heavily processed, transformed by the extreme physics of the bounce, but it might not be completely erased. The distribution of matter and energy at the bounce might reflect, in some highly encrypted form, the state of the matter that fell into the black hole. This raises wild possibilities. Could advanced civilizations send information into black holes, knowing that this information would seed new universes? Could the initial conditions of our universe contain a message from the parent universe, a kind of cosmic paleontology that we might decode if we understood the physics well enough? These ideas stray far from established science into the realm of speculation, but they're intellectually intriguing questions that emerge naturally from the black hole universe scenario. White holes. The other side of the bridge. In the mathematics of general relativity, black holes have a theoretical counterpart called white holes. While a black hole's event horizon marks a region you can enter but never leave, a white hole would have a horizon you could leave but never enter. White holes would be regions of space-time that explosively expel matter and energy. The time reverse of black holes swallowing matter. Einstein's field equations are time-symmetric. For every solution that describes a collapsing star forming a black hole, there's a time-reversed solution describing a white hole that formed in the distant past and is now expanding. The interior of a black hole, in these solutions, connects to the interior of a white hole through a structure called an Einstein-Rosen bridge, more popularly known as a wormhole. In the simplest versions of these solutions, the wormhole connecting black and white holes is non-traversable. It pinches off faster than light can cross through it. Anything that entered from either side would be destroyed at the singularity that forms where the throat of the wormhole collapses. But in more elaborate solutions, particularly those involving rotating black holes described by the Kerr metric, there are scenarios where the wormhole might connect different regions of space-time in more complex ways. Some interpretations of the black hole universe scenario suggest that the new universe created inside a black hole might emerge from a white hole in some other region of space-time, perhaps in another part of the parent universe, or perhaps in some entirely different universe within the multiverse. The big bounce that creates the new universe would, from another perspective, be the white hole explosion that births it into existence. This is highly speculative and faces significant obstacles. White holes are not observed in nature. If they existed, they would be conspicuous, constantly emitting matter and energy. Astrophysicists would easily detect them. The fact that we don't see any white holes suggests either that they don't exist, or that they existed only in the very early universe and have long since evaporated or decayed into other structures. One possibility is that the Big Bang itself was a white hole, the emergence of our universe from a bounce inside a black hole in a parent universe. In this view, what we call the Big Bang was actually the white hole explosion that marked the beginning of our cosmos as viewed from within. The cosmic microwave background radiation, the thermal glow left over from when our universe was hot and dense, would be the radiation from that primordial white hole event, stretched and cooled by billions of years of cosmic expansion. This interpretation faces challenges, particularly regarding the formation of the event horizon. A white hole horizon needs to form before the white hole can exist. But in reverse time, this means the horizon would need to disappear, and it's not clear what physical process could make an event horizon disappear. These are deep technical issues that remain unresolved in current theories. Nevertheless, the mathematical connection between black holes and white holes through Einstein-Rosen bridges suggests that there might be deep links between the singularities at the centers of black holes and the singularities at the beginning of universes. If quantum effects smooth out these singularities and replace them with bounces, then the distinction between black holes and white holes might become blurred, with both representing different perspectives on the same underlying transition from one universe to another. The information paradox and black hole interiors. Any discussion of black hole interiors must contend with one of the most famous puzzles in modern physics, the black hole information paradox. The paradox arises from a seeming contradiction between general relativity, which describes black holes, and quantum mechanics, which describes the behavior of information. In quantum mechanics, information is never destroyed. The state of a quantum system at any moment in time completely determines its state at all other times, both past and future. Evolution in quantum mechanics is unitary, meaning that information is preserved. If you know the exact quantum state of a system now, the laws of physics allow you to calculate what that state was in the past or will be in the future, at least in principle. But black holes seem to destroy information. According to classical general relativity, anything that falls into a black hole is crushed at the singularity, erased from existence. The information about the quantum state of the infalling matter appears to be lost. Stephen Hawking made the problem even more acute when he discovered, in 1974, that black holes aren't entirely black. Due to quantum effects near the event horizon, black holes emit thermal radiation, now called Hawking radiation. This radiation carries energy away from the black hole, causing it to slowly evaporate. Over immense timescales, vastly longer than the current age of the universe for stellar mass black holes, a black hole would completely evaporate, leaving only a faint wash of thermal radiation. But here's the problem. Thermal radiation is random, featureless. It contains no information about what fell into the black hole. If a black hole forms, consumes matter, and then evaporates completely via Hawking radiation, where did the information about the infalling matter go? It can't have escaped in the Hawking radiation, which is thermal and uncorrelated with what fell in. It can't remain in the black hole, which has evaporated away. It seems to have been destroyed, violating the unitarity of quantum mechanics. This is the information paradox, and it's been one of the central puzzles in theoretical physics for 50 years. Various solutions have been proposed. Some physicists argue that information does escape in subtle correlations in the Hawking radiation that we haven't properly understood yet. Others suggest that information is preserved in some kind of remnant left behind when the black hole evaporates. Still others propose that information escapes through quantum entanglement with the Hawking radiation in complicated ways that require a radical rethinking of space-time. The black hole universe scenario offers a different perspective on the paradox. If the information that falls into a black hole passes through the bounce and seeds a new universe, then, in a sense, the information isn't destroyed. It's transferred to the child universe. From the perspective of the parent universe, the information is lost, hidden behind an event horizon, and eventually radiated away as thermal Hawking radiation. But from a God's eye view of the entire multiverse, the information is preserved, just moved to a different branch of the cosmic tree. This doesn't completely solve the information paradox as traditionally formulated, which concerns the perspective of observers in the parent universe who watch a black hole evaporate. But it suggests that the paradox might be resolved by expanding our perspective to include the full structure of the multiverse rather than focusing on a single universe. Moreover, if the Einstein-Cartan theory or similar approaches are correct, and there is no singularity where information can be destroyed, then the classical assumption that information is crushed out of existence might simply be wrong. The information would pass through the bounce and into the new universe, resolving the paradox in a straightforward way, at least from a multiverse perspective, living inside a black hole. Could this be our universe? Let's turn the question around. Could our universe, the cosmos we inhabit, actually be inside a black hole in some larger parent universe? It's a dizzying thought, but one that's worth taking seriously given the physics we've discussed. First, let's consider what this would mean. It wouldn't mean that we're somehow compressed or confined. From our perspective, the universe is vast, containing hundreds of billions of galaxies, each with hundreds of billions of stars stretching across billions of light years. Space is expanding, carrying distant galaxies away from us at ever-increasing speeds. We experience 3 dimensions of space and 1 of time. Causality flows from past to future, and physics operates according to well-tested laws. All of this would be true whether our universe were a standalone cosmos or the interior of a black hole in a parent universe. The key insight is that being inside a black hole doesn't mean being crushed or confined from the inside perspective. It means being in a region of space-time that's causally disconnected from some larger outside region. If we're inside a black hole, the event horizon that separates us from the parent universe would be at the Big Bang, or more precisely, at the Big Bounce that created our universe. The expanding universe we observe would be the natural evolution of space-time following that bounce. The cosmic microwave background radiation would be the thermal glow from the hot, dense state near the bounce. The expansion would be driven by the energetics of the bounce and by the dark energy that appears to pervade our universe. From this perspective, the Big Bang wasn't the absolute beginning of everything. It was a transition, a bounce from a prior state of contraction in the parent universe to a state of expansion in our universe. The before that we can't access or describe using our physics would be the region on the other side of the event horizon, in the parent universe, where different physics might apply. This could potentially explain some puzzling features of our universe. The flatness problem, why the geometry of the universe is so close to flat Euclidean geometry, might be naturally explained if the universe emerged from a black hole. The horizon problem, why regions of the universe that appear never to have been in causal contact with each other have the same temperature and properties, might be explained by the physics of the bounce, which could have causally connected these regions before they were separated by the expansion. The matter-antimatter asymmetry, the fact that our universe contains matter but very little antimatter, might have arisen during the bounce from processes involving torsion and spin that preferentially created particles over antiparticles. The seeds of structure, the tiny density fluctuations that grew into galaxies and galaxy clusters, might have been imprinted during the bounce, perhaps, reflecting quantum fluctuations in the collapsing matter or random variations in the torsion field. There are also potential observational signatures. As mentioned earlier, a rotating parent black hole might induce a preferred direction in our universe, which could show up as anomalies in the cosmic microwave background. The overall topology of space might be non-trivial if the black hole interior connects back on itself in complicated ways, though current observations suggest the universe is very close to being spatially flat on large scales. Some researchers have even looked for more exotic signatures. If the parent universe contains matter and energy that fell into the black hole at different times, this might create inhomogeneities in the initial conditions of our universe that could be detectable as specific patterns in the distribution of galaxies, or in the primordial gravitational wave background. So far, no definitive evidence has emerged to confirm or rule out the hypothesis that we're living inside a black hole. The idea remains speculative, but it's not wildly inconsistent with what we observe. It's a possibility that's worth taking seriously as we develop better theories of quantum gravity and more precise observations of the early universe. Philosophical implications. Meaning in an infinite multiverse. If the black hole universe scenario is correct, it has a profound philosophical implications for how we think about existence, meaning, and our place in the cosmos. Consider first the sheer scope of reality implied by this picture. Every black hole contains a universe. Every universe contains black holes. The structure recursively iterates, creating an effectively infinite multiverse, a vast tree of universes branching and proliferating without end. The number of universes, the number of galaxies, the number of stars, the number of planets, all become meaningless in their enormity. Infinity upon infinity. In such a cosmos, our universe is not special. It's one branch among countless branches, one universe among infinite universes. Earth is an ordinary planet orbiting an ordinary star in an ordinary galaxy in an ordinary universe. From a cosmic perspective, nothing that happens here has any significance. Civilizations rise and fall. Stars are born and die. Even entire universes bloom and fade, and none of it matters to the larger multiverse. This thought can be depressing, a kind of cosmic nihilism. If we're so insignificant, if our entire universe is just one bubble in an infinite foam, what's the point of anything we do? Why does it matter how we live our lives, what we create, what we discover? But there's another perspective, equally valid and perhaps more life-affirming. The black hole universe scenario suggests that creation is built into the fabric of reality itself. Every collapse creates a birth. Every ending is a beginning. The universe is not running down toward a final heat death. Instead, it's constantly regenerating, creating new universes, new possibilities, new chances for complexity and consciousness to emerge. Moreover, the scenario suggests a kind of cosmic inheritance, a connection between parent and child universes. The physical constants of a child universe might be similar to those of its parent, with small random variations. Universes that are good at creating complexity, at forming stars and galaxies and structures where interesting physics can happen, would produce more black holes and thus more offspring universes. Over the generations, the multiverse would be populated primarily by universes conducive to complexity. In this view, we're not isolated accidents, random fluctuations that happened to allow consciousness in an otherwise dead cosmos. We're part of a lineage, descendants of a long chain of parent universes, each of which had properties that allowed it to create black holes, and thus to reproduce. Our universe's seemingly fine-tuned constants might reflect this evolutionary history, the result of countless generations of cosmic natural selection. There's something almost hopeful in this picture. It suggests that the universe is not just a place where complexity occasionally arises by accident, but a place where complexity is actively propagated, selected for, encouraged. The multiverse is fertile, creative, generative. New universes are being born constantly, each one a fresh start, a new roll of the cosmic dice, a new chance for something interesting to happen. It also changes how we might think about advanced civilizations and their long-term goals. If you are a highly advanced civilization with access to tremendous energy and technology, and you understand that black holes create new universes, what might you do? You might try to engineer black holes with specific properties, knowing that these would seed universes with particular characteristics. You might even try to encode information in the matter you send into black holes, information that would influence the initial conditions of the resulting universes. This is wildly speculative, bordering on science fiction, but it's not completely absurd given the physics. An advanced civilization might view black hole creation not as an ending, but as a form of cosmic propagation, a way to spread order, complexity, and perhaps even life itself to new universes. They might be gardeners on a cosmic scale, planting seeds that would flower into entire universes. From this perspective, our own universe's initial conditions might contain signatures of such engineering from the parent universe. The fine-tuning of constants, the specific pattern of density fluctuations in the early universe, might not be random at all, but carefully designed to maximize the chances of interesting physics and chemistry, and eventually life. We might be, in a very real sense, the children of some parent civilization that created the black hole in which our universe exists. This is pure speculation, of course, and there's no evidence for it. But it illustrates how the black hole universe scenario opens up new ways of thinking about cosmic origins and cosmic purposes. The journey complete. Emergence and rebirth. Let's return to our journey, to you, the intrepid explorer falling into the black hole. We left you approaching the singularity, the place where classical physics predicts infinite density and infinite curvature, where space and time themselves lose meaning. But in Einstein-Cartan theory, you never reach a singularity. As the density of space-time around you increases, as the tidal forces intensify and space-time curvature becomes ever more extreme, a new force emerges. The torsion of space-time, coupled to the spin of the particles that constitute you and your spacecraft, generates a repulsion. This is not something you could feel directly, not a force pushing on your body in any conventional sense. It's a modification of the geometry of space-time itself, a tendency for the extreme curvature to reverse, to unbend, to bounce. The experience would be impossible to describe in familiar terms because nothing in our everyday world, nothing even in the extreme environments we've explored in our universe, from the centers of stars to the collisions of atomic nuclei, approaches the conditions you're experiencing. Space and time are fluctuating wildly at quantum scales. The distinction between before and after becomes fuzzy. Causality itself becomes probabilistic, quantum mechanical. But then the bounce, the contraction reverses. Space-time begins to expand again, but not back into the universe you came from. That direction is closed off by the event horizon, by the structure of causality that makes the singularity an inevitable future. Instead, the expansion opens up new space, new time, a new region of space-time that inflates rapidly, driven by the tremendous energy density of the bounce. From your perspective, if your consciousness could somehow survive this process intact, which is unlikely, but let's imagine it for the sake of the narrative, you would find yourself in a strange new environment. The oppressive curvature would be easing. The tidal forces would be subsiding. Space would be expanding around you, rapidly, exponentially at first, then settling into a more measured expansion. As the universe expands, it cools. Energy that was concentrated in extreme curvature and torsion transforms into particles and radiation. The physics of the early moments would follow a sequence perhaps similar to the early history of our own universe. First, a quark-gluon plasma, too hot for protons and neutrons to exist. Then, as cooling continues, quarks bind into nucleons. After a few minutes, conditions would be cool enough for nucleosynthesis, the formation of light atomic nuclei like helium and lithium from the primordial hydrogen. After about 380,000 years, the universe would cool enough for electrons to combine with nuclei to form neutral atoms, a process called recombination. At this point, the universe would become transparent to light for the first time. Photons that had been constantly scattering off free electrons could now travel freely, creating what would become the cosmic microwave background radiation of this new universe. Over hundreds of millions of years, small density fluctuations, quantum variations imprinted during the bounce, would grow under gravity. Regions slightly denser than average would attract more matter, becoming denser still. Eventually, these overdensities would collapse into the first stars, massive, brilliant objects that would flood the universe with light, ending the cosmic dark ages. These first stars would forge heavier elements in their cores through nuclear fusion. When they exhausted their fuel and exploded as supernovae, they would scatter these elements into space, enriching the gas from which later generations of stars would form. Those later stars would have planets, some of them rocky worlds with atmospheres and oceans, places where complex chemistry could occur. And on some of those worlds, eventually, perhaps life would emerge. Simple, self-replicating molecules would give rise to cellular organisms. Evolution would generate complexity, diversity, adaptation. After billions of years, some lineages might develop nervous systems, then brains, then consciousness, then intelligence. These beings would look up at their night sky and wonder, just as we do, about the nature and origin of their universe. They would have no direct knowledge of you, of the explorer who fell into a black hole and whose journey catalyzed the creation of their entire cosmos. The information about your specific identity, your memories, your thoughts, would have been scrambled beyond recognition by the bounce. But in a very real sense, you would be their progenitor, the seed from which their universe grew. This is the ultimate transformation suggested by the black hole universe scenario. What looks like death, the inevitable crushing destruction at a black hole singularity, might actually be rebirth on the most cosmic scale imaginable. Your fall into the black hole, your dissolution in the extreme physics near the bounce, would be the beginning of a new universe, a new timeline, a new chapter in the infinite story of the multiverse. Conclusion: the cosmos as creative process. We've taken quite a journey tonight, from the calm of our opening meditation to the edge of a black hole, through the event horizon, to the singularity that turns out not to be a singularity at all, but a bounce, a transition, a birth. We've explored ideas at the cutting edge of theoretical physics, places where general relativity meets quantum mechanics, where mathematics dances with speculation. The black hole universe scenario, whether ultimately proven correct or not, offers us a remarkable vision of what reality might be. It suggests that the universe is not a closed system running down toward entropy and heat death, but an endlessly creative process, constantly generating new universes, new possibilities, new homes for complexity and consciousness. It reframes destruction as creation, endings as beginnings. It suggests that even the most extreme gravitational collapse, the most complete annihilation imaginable, might be a form of cosmic reproduction, a way for the universe to reinvent itself, to explore new configurations of physical law, to try out new experiments in the laboratory of existence. If we live in such a cosmos, then we're part of something far grander and stranger than traditional cosmology imagined. We're not isolated observers in a single universe that began with a mysterious Big Bang and will end in a lonely heat death. We're participants in an infinite multiverse, a vast tree of universes branching and proliferating, each one connected to its parent through the bridge of a black hole, each one potentially giving rise to children of its own. This vision doesn't answer all our questions. It arguably raises more questions than it answers. How did this process start? Is there a first universe, a root of the tree, or does the chain extend infinitely into the past? How much variation is there between universes? Do they all share the same basic laws of physics, just with different constants, or can the laws themselves vary? If universes can be engineered by advanced civilizations manipulating black hole formation, what ethical frameworks govern such cosmic-scale creation? These are deep questions, and we're only beginning to develop the tools and concepts needed to address them. The physics of quantum gravity, the theory that will ultimately describe what happens at black hole singularities and in the first moments after a universe is born, remains elusive. String theory, loop quantum gravity, Einstein-Cartan theory, and other approaches all offer insights and predictions, but none has been definitively confirmed by experiment. Yet the mere fact that we can ask these questions, that we can construct mathematically consistent models of black holes giving birth to universes, that we can compute predictions and imagine tests, speaks to the remarkable power of human reason and imagination. We are contemplating the nature of reality on scales both infinitesimally small, the Planck length, where space-time becomes quantum foam, and incomprehensibly large, an infinite multiverse of universes. We're using mathematics and physics to peer beyond the boundaries of our observable cosmos, to imagine what lies hidden inside black holes and what might have come before our Big Bang. This journey we've taken tonight is ultimately an exploration of possibility, of what might be true rather than what must be true. The honest answer to the question, what happens if you fall into a black hole, is that we don't know for certain. Classical general relativity gives one answer. You'd be spaghettified by tidal forces and crushed at a singularity. Quantum theories of gravity suggest modifications. Perhaps the singularity is smoothed out by quantum effects. Perhaps information is preserved. Perhaps the collapse reverses in a bounce. The scenario where black holes give birth to new universes is one possibility among several. A compelling vision that emerges from Einstein-Cartan theory, and similar approaches, but not yet established fact. It might be that black holes are simpler than this scenario suggests, that they're truly just endpoints where matter is compressed to oblivion. Or it might be that they're even stranger, doorways to wormholes or portals to other dimensions or something we haven't even imagined yet. But whether or not black holes literally create new universes, the exercise of exploring this possibility teaches us something valuable. It shows us that the universe might be far more creative, far more generative, far more interesting than even our wildest imaginings. It reminds us that the deepest mysteries of existence, questions about cosmic origins and ultimate fates and the nature of reality itself, are still open questions, still frontiers of human knowledge waiting to be explored. So, as we come to the end of our journey, let's hold on to that sense of wonder, that openness to possibility. The cosmos is stranger than we know, stranger than we can know, and every answer we find opens up new vistas of questions. Black holes, those most extreme and exotic of cosmic objects, might be not just destroyers but creators, not just endings but beginnings. And perhaps, just perhaps, we're living inside one right now. Inhabitants of a universe that bloomed from a black hole bounce in some parent cosmos, destined to create our own black holes that will birth universes of their own, an infinite chain of cosmic creativity stretching forward and backward through the multiverse. If you found this journey through the mysteries of black holes and the possibility of cosmic rebirth intriguing, please consider liking this video and subscribing to the Science Pillow. Your support helps me continue exploring the boundaries of science and imagination, bringing you more journeys to the edge of what we know and beyond. Let me know in the comments what cosmic mysteries you'd like to explore next. For now, let yourself rest. Let the strangeness and wonder of these ideas wash over you like waves lapping at a shore. The universe is vast and strange and beautiful, full of mysteries that dwarf our understanding. And somehow, impossibly, we're here to witness it, to explore it, to ask questions and imagine answers. Sleep well and dream of infinite universes